Hey everyone. Today we're going to tackle one of the most powerful and, believe it or not, surprisingly simple tools in all of engineering and physics. We're talking about the Laplace transform. So let me ask you a question. How do you X-ray a function? How do you actually look past its surface to see what it's really made of? It's kind of like trying to figure out how a car engine works just by watching the wheels spin. You can't really see what's going on inside. Well, it turns out that a lot of the most important functions we see in physics and engineering they're really just combinations of simpler, more fundamental ingredients. And the secret ingredient? It's exponential functions. That's what they're all built from, deep down. Now, you could just learn to use the Laplace transform like you learned to drive a car, right? You just turn the key and go. No idea what's happening under the hood, but that's not what we're about here. Today, we are absolutely popping open that hood. We want to see the beautiful machinery inside and really understand how it works. All right, let's get to it. Time for that function X-ray. And the machine we're going to use to do this is, yeah, you guessed it, the Laplace transform itself. Okay, so what is this thing? Put simply, the Laplace transform is like a mathematical machine. You feed it a function, one that depends on time, we usually call it f of t, and it processes it. Then it spits out a completely new function, which we call f of s. And this new function, this is where all the hidden secrets are. Let's just walk through this. Think of it as a super simple three-step process. Step 1, you start with your input, some function of time, f of t. Step 2, you feed that function into our Laplace transform machine. And step 3, the output. This is the amazing part. What comes out is a brand new function, f of s, which is basically a secret map of the original. Okay, so a secret map? What does that even mean? What is this map actually showing us? Let's decode this thing. So this map of ours, it lives on a special kind of graph that engineers and mathematicians call the S-plane. And when we plot our new function, f of s, on this plane, something really cool happens. We often see these incredibly sharp, almost infinite spikes just shooting up. These spikes, they are the key to everything, and they have a special name. We call them poles. And this, right here, is the entire point. This is the big reveal, the location of these poles on our map. It tells us exactly which exponential ingredients were used to build our original function. This is the X-ray we've been looking for. It's the answer. So this brings us to the most crucial point, the one golden rule. Seriously, if you remember just one thing from all of this, make it this right here. Okay, so if your original function is a simple exponential, let's say e to the power of at, then its secret map, its Laplace transform, is going to have one single sharp pole. And where is it? It's located precisely at s equals a. See? The location of the pole is the number that was up in the exponent. It's that simple, that direct. All right, let's see this in action with something you already know, a simple cosine wave. Now, a cosine wave doesn't look exponential at all, right? But here's the secret. It's actually built from two very specific exponential ingredients. So if we follow our golden rule, its map should have what? Two poles, right? And guess what? It does. You get one pole at s equals I and another one at s equals negative I. The transform finds both of those hidden ingredients perfectly. It's amazing. Okay, finding hidden exponentials it's pretty cool, for sure. But why does this actually matter in the real world? What's the point? Well, this is where the Laplace transform goes from being just a neat mathematical trick to being an absolutely revolutionary tool. Here it is. The Laplace transform's greatest magic trick is this. It turns messy, horrible, difficult calculus problems into simple algebra. It literally takes the hardest part of solving things like differential equations and just makes them totally manageable. Just look at this table. It shows the magic perfectly. On the left, before the transform, you're wrestling with a differential equation. That's calculus. It's tough. But on the right, after the transform, you just have a simple algebraic equation. And check this out. The most difficult operation, taking a derivative, it just gets replaced by simple multiplication. You just multiply by s. This literally can turn hours of complex calculus into just a few minutes of straightforward algebra. It's a total game changer. So let's take a step back. What have we really learned here? Let's zoom out and just appreciate the new perspective this whole process gives us. Okay, let's tie it all together. The Laplace transform, it's like an X-ray for functions. It creates a special map for us on something called the S-plane. On that map, we get these spikes called poles, and they pinpoint the exact location of a function's hidden exponential ingredients. And the ultimate payoff, the whole reason we do this, is that it transforms brutally hard calculus problems into much, much simpler algebra. So you see, in the end, the Laplace transform is really more than just a math tool. It's this powerful demonstration of a bigger idea, that just by changing your perspective, by transforming a problem into a different world, you can make something that seems impossibly difficult become fundamentally simple. And that really leaves us with one final thought, doesn't it? What other complex problems out there, maybe even in our own lives, could be solved if we just found the right way to change our perspective? Something to think about. Thanks so much for joining me on This Explainer.